We introduce a simple multi-scale shape from shading method that takes two images from the same viewpoint and produces a textured height field. We call this surface depth hallucination and validate it perceptually. We start by taking a pair of images, one diffuse lit and one flash lit. We use these to obtain an albedo map and an estimated depth map. Once we have both maps, we can render a textured height field with novel viewpoints and lighting. Our method has the big advantage that it has a very simple data capture process and uses cheap equipment. We simply take pictures of the same scene with diffuse lighting, for example on a cloudy day or in shadow, and with a flashlight. An albedo map is calculated by subtracting the two images and dividing the result by a calibration image to correct for vignetting. To simplify data capture, if we already have a similar example that we have applied our method to, we can capture just a single image and then approximate albedo and diffuse shading using histogram matching. To hallucinate depth, we first acquire a shading image by taking the ratio of the diffuse lit image and the albedo image. We can infer the surface mesostructure by thinking of it as a terrain with hills and valleys. Both models are unified by making some simplifying assumptions. Shading on the hills can be approximated as shading of hemispheres, while shading in the valleys can be thought of as being similar to cylindrical wells. We perform this process over multiple scales to adapt our model based on the size of image features and combine our depth estimates at each scale. We progressively blur our diffuse shading image up to a maximum detail size based on image content. At each level, the image is divided by the next level of blur, effectively giving a Laplacian pyramid of equal resolution images. We apply our depth function to each level, arriving at a per pixel depth value. Once we have an albedo map and a depth map for our surface, we can apply any rendering technique. In this animation, we see a standard textured surface without 3D surface detail. We simulate a full lighting cycle from noon till noon the following day. Notice as the hours change, we see no progression of shadows. In the oblique view, we add the depth information estimated with our method. Notice how shadows begin to appear. An animation of the solar position changing overhead shows shadows moving across the surface. Finally, we show that our shading is also plausible as we change the view. We can see how the surface mesostructure gives realism to the animation compared to simple texture mapping. Here is another example of our results. This time the solar position is fixed, but the surface is rotated. We use the radiance physically based renderer to generate our final results. We validate our results with two user studies. In one study, we show participants pairs of images. This study validates the visual plausibility of our depth estimation compared to ground truth data. Each pair of images contains one picture rendered from a laser-scanned depth map and one rendered from our hallucinated depth map. We ask participants to choose the one they believe is more likely to be the real surface. Participants were unable to discriminate between both simulations. In the other study, we sequentially show participants a set of high-quality images containing both photographs and synthetic images. You are seeing a sample of these images now. Participants were asked to rank the images based on their certainty that the image was a photograph. We showed a total of 27 images in a randomized order consisting of 9 photos, 9 synthetic images created using paired input images, and 9 created by a single input image histogram matched with a similar exemplar. Participants were asked to rate the authenticity of each image on a scale from 1 to 5, the midpoint 3 meaning people could not decide. Average ratings for photos were higher. However, we found that 75% of participants rated the synthetic images as being more likely to be photographs than synthetic images. 2/3 of the images you saw were fakes. Did you spot them all? In summary, we have presented a practical, simple, low-cost and effective multi-scale shape from shading method to create plausible textured surfaces suitable for increasing the realism of architecture, games and special effects applications.